Thank you for the introduction. I'm very happy to be here. Since this is an industry session, I'm going to talk about something that I think most of our industry collaborators are interested in. We know that computer software is everywhere, is playing a central role in almost every aspect of human society. But the software in company is different from software students develop in school, right? If you're in school, you just do a programming assignment, and then after the semester ends, you toss it. But if it's in industry, we have already, like the company invested some employer money, salary into that software. They want it to stay. And over time, the software will age. People keep adding features into it. It's no longer, the implementation no longer in the best structure it could have been if it's implemented from scratch. And there's people who join the company, people who leave. Over time, no one understands the code anymore. So this is a large problem in almost every industry collaborator we talk to. And what happens when we want the software to stay and then it ages? We want it to be stable. As a concise example of this sentiment, Facebook, now it's called Meta. 11 years ago, they changed their internal model from move fast and break things into move fast with stable infrastructure. So if the code still works, please don't touch it, right? If you touch it, it will break. And if you want to change it, please do it slowly and carefully. And then what happens if we want the software to remain stable? We will be changing it not just a little bit slower, but a lot slower. Here's what happens. If we don't want to break the code, look at what's happening with the US government. So in 2019, they were using software that were like 50 years old. Some of them written in ancient programming languages like COBOL. They were serving critical tasks while having high security issues. And why is this piece of software still around? It's because people don't want to throw it away, right? People have already invested so much care into developing this software. We're not gonna just throw it away, right? We're going to keep using it, but it's very hard to come up with a better version for it. It's so complicated. Yeah, and there are some serious societal impact, right? During COVID-19 outbreak in 2020, there's this news media, some state governors said that they literally needed COBOL programmers to help them maintain the employment data. That's just one example. Another example is in China. The news article is in Chinese, but I translated it in English. It says a train management system suddenly went down because the deprecated Flash player terminated support. And at the time, their very urgent solution was to downgrade their Flash version. This way, they can embrace all of the security vulnerabilities in the deprecated Flash player, but it's more important to keep it running. So, I mean, from there's just a few examples. People are stuck with outdated software infrastructures because it's so hard to move them. Similar things in, I think this is from the UK, or about financial services and retail. There has been a lot of ongoing effort on preserving or reusing human knowledge in software, and they're having a hard time. As we can see, automated software like migration or translation across different platforms or like different programming languages, this is in general a very difficult problem. This is a quote from a paper that's published 25 years ago. People have already realized that it's an extremely hard problem. Many people have already tried, but few have succeeded in changing the languages or platforms for existing software. So in this talk, I'm going to tell you about our recent work on several automated techniques for extracting, transforming, and augmenting software functionality. So the goal is to make the software execute in different computational environments And once if we have this automation, we can have a lot of benefits, like making it, like take advantage of the modern technologies, make it run faster, be more secure. We can have better code for et cetera, et cetera. And our goal is to enable us to automatically exploit the benefits from human knowledge in software. So if you draw it in a diagram, we want to take an existing program and have some automated way to give you new, better software. Hopefully the new software will do exactly the same thing as before, so we get the stableness, but at the same time, we want it to do it in a potentially better way. For example, use a better language, a better platform. And because this is a very difficult problem, we need a key insight, which is to target specific computational domains. So if you just remember one point from this talk, I want you to remember that we're doing it in a domain-specific way. So think of it like if you're learning about compiler optimization, every single optimization pass is doing a very simple thing about one possible pattern in the code. But if we have like 100 different optimizations, like combine them, then it becomes very powerful. And similarly, for this very difficult problem of program migration, we are also going to do it one domain at a time. So if we do this, have this insight, then it means that we need to choose the computational domain very carefully so that we balance the feasibility of our algorithm and the generality of the solution. If we do this in a domain-specific way, we're going to have a chance to get correctness guarantees, even though it's a very difficult problem. And more broadly, the intuition is that we're going to encapsulate the domain expertise for large-scale reuse. I'm going to talk about 3 pieces of work that of our ongoing and past research. And the overarching theme is that we are taking advantage of domain knowledge. So the first one I'm going to talk about is called Conure. It is named after a kind of parrot, and you'll soon realize why it's the case. So this system called Conure is designed to do this. This is something we call program inference and regeneration. We take an existing program and we treat it as a black box. So imagine the case where we have a piece of code. We don't want to read the code because it's so ugly, but it still runs, right? As long as it runs, we keep it, right? So because it still runs, we are going to have an algorithm to run the program, treat it as a black box, and then we just observe its externally visible behavior and infer a model of the program functionality. Then from that model, we generate brand new code. The new code is going to be cleaner, of course, right? Or it can also use a different language, for example. So this approach, because it treats the original program as a black box, there are several advantages, right? It can use the original program, it can be obfuscated, it's fine. It can use multiple programming languages, it can use any programming styles, it can be written like 50 years ago, it doesn't matter. As long as it runs, it works. So how do we make this happen? This is a very difficult problem in general, right? But how do we do it in a domain-specific way? We look at this important domain of data retrieval programs. So these kinds of programs are prevalent. Here, a user interacts with the program through interfaces such as command line arguments or a web browser. And then when the program runs, it sends SQL queries to an external database, and the database returns data. They have these interactions, and then eventually the program returns an output to the user. So these kinds of programs are widely used for multiple decades. They're still prevalent today. There is a long-standing need for automated understanding, regeneration, and development, and security, et cetera, about these kinds of important applications. So think about those like banks or like web forums, blogging apps, all those kind of stuff. And then two common characteristics. One is that the implementations can be potentially very complex. And the other is that if you look at their core functionality, it can be kind of simple. Like it's just storing and retrieving data in some sense. So we take advantage of these observations to come up with an algorithm that works very well for this kind of programs. So here's our system. It's called Conure. We start with the input parameter format and the database schema that are provided by the user. With this information, we populate the database with chosen values, and we run the program with chosen inputs. And when the program runs, we use a transparent proxy in front of the database to intercept the traffic. So this is one of the places where we use the domain knowledge, because we know there are strong boundaries between the computational component and the database, so that's what we can have some extra observations, meaningful observations at their boundaries. And after the program terminates, it also produces an output, so we collect the output as well. And we do this interaction multiple times using carefully chosen inputs. And at the end, we use the inferred model to generate a new program. So here, the most difficult and the most interesting part is how we generate these interactions to infer the program functionality. And here's how we do it. We use domain knowledge about data retrieval programs, and we crystallize that domain knowledge into a DSL, a domain-specific language. So one part is the data flow. So we assume that in these kinds of programs, every statement performs a query. You can select data from several joint tables to satisfy an expression, and with the retrieved data, you can store it in a variable which can be referenced later in the program. That's about data flow. Second component is the control flow. So we assume that there are two kinds of control flow in these kinds of programs. An if statement, a conditional statement, looks at whether a query retrieves empty data or not. And a loop just iterates over the rows retrieved by a query. So these kinds of data flow and control flow are very commonly seen in database-backed applications. So intuitively, if we concretize these kinds of domain knowledge into a DSL, and if we design an algorithm just for this DSL, it means that we can use some nice characteristics, nice properties. For example, here, because we are the control flow is directly tied to the query results, it means that if we choose the inputs and database values very carefully, then we have a chance to force the program execution down a certain path that we want to look into. So here's an example program that belongs to that can be expressed by this DSL. It has two input parameters, a student ID and a password. It has some database tables about students, teachers, courses, and registration. And what the program does is that it first checks if a student exists. If the student exists, it checks its password. And if the password is correct, then it retrieves the course registration records for that student. So this is an example program. In our algorithm is designed together with this DSL. In the algorithm, we formulate a hypothesis about what we have learned and we still don't know about the program. So for example, here is a hypothesis. It has a non-terminal symbol proc. It means that we currently know nothing about the program except that we have assumed that it can be expressed by our DSL. Here's another example hypothesis. It says we know that the program starts with three sequential statements, but we don't know what happens next. Here's another hypothesis. It says that the program starts with a loop. The loop contains a conditional statement, and in the conditional statement, the first branch is empty, but we don't know about the second branch, and also we don't know what happens after the loop. So the algorithm is going to resolve each of the proc non-terminal symbols by applying an appropriate production in our DSL. On the top left is the grammar for our DSL, and on the right, this is the initial hypothesis we start with. And next, our algorithm is going to choose those input values and database values to set the program to run it and collect the database traffic. And from there, we infer the program by resolving the non-terminal symbol. So for example here, we run the program with student ID 0 and password 1. And it turns out, and the database contents was empty. So in this case, there are no students in the database. Therefore, the initial conditional check did not pass. And therefore, the program just terminates after sending one database query, which retrieves 0 rows. So from this observation, we can get rid of the first production. The production says the program is empty, but of course, the program is not empty because it retrieves because it sent a query to the database. Say we observe another execution where we changed the student ID and password so that the student exists, but the password is incorrect. So if we look at both executions, then we can get rid of the the animation says if we try to look at a third execution first. The third execution asks whether there exists a way to make the first query retrieve at least two rows. It turns out to be unset, so the execution E2 does not exist. And with this information, we can get rid of the production that says there's a loop. And because of the first two executions, we can get rid of the production that says it's a sequential statement. So there's only one production left. That's about the conditional. That's why we expand the hypothesis into something on the bottom right. It says that the program has a conditional. It first performs a query, but we don't know about the two branches yet. So the algorithm is going to continue. And for each proc non-terminal symbol, it's going to recursively expand it with an appropriate production that we conclude from generating multiple executions of the program. And for each, to figure out each of the production, we generate those inputs and database values to force the program into that specific path. So for example, here we need to ensure that the first query returns non-empty, the second query returns non-empty, and the third query returns non-empty as well. So intuitively, we can feed this information into a solver, which can help us figure out the appropriate input and database values. So intuitively, each set of chosen input and database values are designed to reveal new information in our hypothesis. So for this algorithm, we have a correctness result given any black box program. As long as it can be expressed in this DSL, then we guarantee to infer a correct program. The proof is by structural induction, and we have the proof in a TOPLAS paper. Some experimental results. We tried this algorithm to several web applications in Ruby on Rails and an application in Java, and we were able to synthesize new implementations in Python. So here our technique builds on the domain knowledge that there's a strong boundary between the program and the database, and that there are some common structures for conditionals and loops. And because this algorithm analyzes only the externally observable behavior, it does not need to access or analyze the source code of the program, and it works well with programs with multiple languages. We have follow-up work that uses a similar strategy to infer and regenerate string processing libraries and stream processing libraries to get more secure, and to regenerate stream processing scripts to make them run faster because of synthesized parallelization. We also have ongoing collaboration with a company to use this strategy to regenerate mobile applications to different languages and platforms. The second approach is about platform migration. So this is a work my student just presented yesterday at UPSA, so I'm going to be really fast on this one. But the point is that it's also solving a very difficult problem by taking advantage of domain insights. So here's the background. We know the user applications we care about run on operating system, and operating system run on hardware. And when we talk to some operating system experts, so for UPSA, for Splash this year, there are like more than 800 attendees, right? So people are very productive inventing programming languages in some sense. But there's another community, operating systems, where people are also very productive. They created so many cool operating systems, but how many of them do you use? No, you don't use any of them, right? You just keep using Windows, Linux, Mac, or whatever. So what's the problem? Why, like, these operating systems are supposed to make our programs run faster, but we're not using them. And the problem is that to make those programs run fast, they require a change to the system called interfaces. So if your program reads files using open, read, and close, if you want to take advantage of those fancy operating systems, you can no longer use them anymore. You have to use the things, APIs like get, put, peek, patch, like the things you don't even understand. And unfortunately, people are reluctant to migrate their programs to use those new APIs. So the research question is how to update the applications to maximize the performance benefits, or in other words, how to automatically migrate programs by changing the I/O APIs. So our goals are to make it automated, to obtain performance improvements and have soundness guarantees. So in this case, we're solving some very difficult challenges by using domain insights. First is semantic mismatch is the problem where the old and new APIs semantics don't really match. So you have to reason about what's missing and what needs to be added. In this case, we're luckily, because we're caring about like file operations in particular, or the I/O APIs. Luckily, in this case, most of the API semantics just talk about like data transfer. There needs to be a source, a destination, and several lengths of bytes that needs to be transferred. So we can model them as those operations at the level of something we call atomic operations, and we formalize the semantics of APIs at that particular level. That's easier to reason about. And secondly, the challenge of complex control flows. So that's the case where we have a sequence of correlated APIs that are scattered in the code. You have some conditional loops and conditional statements, some loops, some nested function calls. In that case, because we know that we care about I/O APIs, if you look at those programs that do file input and outputs, they have some common patterns. For example, their conditionals are usually just error handling. And if you look at their loops, usually they're just a loop that says, please transfer all those bytes, or go iterate over the entire buffer. And if you look at those functions, they're usually just abstractions, like in addition to calling the open API, please also check these additional flags, those simple function wrappers. So if we take into account those kinds of domain knowledge, we can simplify the code structure a lot and make the migration much more tractable. The third challenge is the interdependence on program states. So once again, we reason about the program semantics and using pointer analysis. And here we are taking advantage of the semantic types that often appear in programs that perform I/O. Okay, so I'm going to skip the technical detail because it's already presented in UPSA. And for the third system about source code refactoring, it's a problem about restructuring source code without changing its external behavior to eliminate code smells and improve readability and maintainability. Traditionally, some existing approaches, there are two kinds of existing approaches. One that guarantees soundness, another one that does not. So once I'm going to talk about the techniques that guarantee soundness because we want in refactoring, you actually want to keep the code to do what it does before. And if you look at those existing techniques that ensure soundness, they usually treat it as a general program synthesis problem. Give me an existing source code, synthesize a new piece of code that's equivalent to the previous one, subject to some given sketch. But we realized that this general approach is not the best way we can do it. We can once again take advantage of some domain insights. For example, if we're just doing data structure refactoring, we can actually figure out a way to find a closed form solution to the refactoring problem without actually needing to go through the heavyweight like solver invocation or synthesis algorithm. So this is still work in progress. But it's cool that we can once again solve a previously difficult problem by using like domain insights. So yes, so here's the summary slide. Our goal is to take an existing program and automatically make it better, in the sense of having a better language, better platform, or better data structures, for example. And this is a very difficult problem in general, but what makes our approach possible is to use domain insights. And in a higher level, we are encapsulating domain expertise for large-scale reuse. So our goal is to capture the maximal benefits from human effort and knowledge in software. Thank you.
Okay, let's thank Professor Shen. Any questions? You can come to the mic.
Hi. I was wondering, this seems very exciting. I was wondering if Konya, like if there are any, what are sort of the limitations of the kinds of programs that maybe, so what kinds of programs could Konya not regenerate, for instance?
It cannot regenerate programs that are not in the DSL. So
yeah.
We designed the DSL and the algorithm together in order to balance the tractability of the program and the meaningfulness, tractability of the problem and the meaningfulness of the programs we can work with. And the middle point we have found is the class of data retrieval programs. But we do have some generalizations to other application domains here. But they're still like well-defined computations. Yes.
I have a quick question for the second work. You mentioned you upgrade DB libraries. Do you find some API compatible bugs in some applications?
We're not assuming that we're not trying to reason about whether the libraries have bugs or not. We're just assuming that given a specification, we have to migrate the user application. So for the DB libraries, we have a section in the paper saying that whatever we do with I/O APIs can be generalized to the database domain for upgrading its libraries and making it run faster, for example. But we didn't really look into what the libraries are how their libraries are implemented.
Okay. Thank you.
Thank you.